This map shows the evolutionary range of Alces alces, the moose. They are a circumpolar species that crossed the Bering Strait into North America roughly 14,000 years ago, establishing a massive footprint across the dense, cold boreal forests of Alaska and Canada. But if we follow the Rocky Mountain corridor south into Wyoming, Utah, and Colorado, we reach the extreme equatorial edge of the species range. The moose here belong to a specific subspecies, the Shiras moose. They are noticeably smaller than their northern relatives. This is an expression of Bergmann's rule, a physiological adaptation where species in warmer climates have less body mass to help dissipate heat. During the 20th century, this smaller subspecies rapidly expanded its range, colonizing Utah and Colorado in a highly successful population boom. Today, that growth has stalled.
In many areas, the numbers have flatlined or dropped, despite these southern habitats having an abundance of forage and a complete absence of apex predators like wolves and grizzlies. To understand exactly why a species stops growing at its physiological limit, we must abandon broad assumptions from its core range in Alaska and instead reverse engineer the localized demographic engine keeping them alive in the south. This is what winter habitat looks like for a Shiras moose. They concentrate in specific riparian corridors to find food during harsh intermountain winters. In this specific environment, traditional top-down population regulators, namely large predators killing adults and calves, are functionally absent. Without predators, bottom-up regulators take over. The population size is dictated by density-dependent resource depletion, how much food is left, severe winter storms, and summer droughts. The limiting factor for population growth at this equatorial edge comes down to a single biological metric: maternal body condition. A female's fat reserves act as the physical bridge between the changing climate and the demographic survival of the herd. To prove exactly how that mechanism works, ecologists must first calculate the strict mathematical baseline of how much energy one individual moose requires to survive. This ledger highlights the strict energetic constraint of a Shiras moose. An adult male requires 1,191 kilojoules of digestible energy per kilogram of metabolic body weight daily. To meet this, they rely almost entirely on riparian willow, comprising 91% of their summer diet. Extracting that energy is entirely dependent on ambient temperature. Moose physiology becomes heavily stressed when summer temperatures exceed 14 degrees Celsius, or 57 degrees Fahrenheit. In the winter, that stress threshold drops to just 5 degrees Celsius. Crossing those thresholds, the animal's foraging behavior shuts down. They abandon daily feeding bouts and retreat into heavy shade to avoid overheating. This thermodynamic limit places a strict ceiling on the environment's ability to support life. It does not matter how much willow is physically present on the landscape if the moose is too hot to stand in the sun and eat it. Combined, these energetic and thermal limits cap the carrying capacity of even premium habitats, like Rocky Mountain National Park, at a maximum of just 0.21 moose per square kilometer. Translating those individual energetic limits into population-level trends requires looking at the specific life history strategy of large, long-lived megaherbivores. In a standard demographic matrix, adult female survival remains rigidly constant, prioritized regardless of environmental stress. Because her survival is mathematically locked, herd volatility is driven almost entirely by fluctuations in reproductive output. The biological middleman that connects environmental energy intake to that reproductive output is maternal body condition, measured specifically via winter rump fat depth. This probability curve maps data from the Utah herds, revealing the mathematical relationship between fat reserves and reproduction. As winter rump fat increases, the probability of pregnancy tracks strictly upward. Even if pregnant, this same fat metric dictates successful spring calf recruitment. It is a brutal physiological trade-off. A female moose will sacrifice her pregnancy or lose her calf rather than compromise her own adult survival when energy is too low. When thermal stress or low forage drops the energetic baseline, rump fat depletes. That quietly shuts down the population's reproductive engine, while the adult females continue to survive on the landscape. Tracking these subtle, fat-driven demographic shifts over the decades is difficult, because the primary data source consists of noisy, imprecise aerial helicopter counts. To find the actual signal in the Utah data from 1958 to 2013, researchers utilize a Bayesian state space model. This filter visually removes noise from scattered raw data points to reveal the true biological population growth, lambda, separating it from simple observation error. Once the noise was stripped away, the model identified two dominant hidden parameters exerting severe negative pressure on lambda. The culprits halting the population growth were not predators. The stall was driven entirely by a toxic combination of high population density and warm winter temperatures. This regression graph maps population size against growth rate, or lambda. During cool winters, we see a moderate downward slope of standard density dependence, but overlaying warm winters reveals a drastically steeper depression of population growth, crossing below the replacement threshold much earlier. The biological reality behind that red line is twofold. First, heat stress forces the moose to stop eating. Second, warm winters increase the survival and prevalence of parasites, specifically winter ticks. Tens of thousands of winter ticks can latch onto a Sioux moose, draining its blood and energy, which severely exacerbates the nutritional deficit. High density and warm winters act as a dual mechanism. Together, they rapidly degrade maternal rump fat, effectively choking the reproductive engine and stalling the population. The vulnerability of the Utah and Colorado herds is part of a continent-wide mathematical rule for moose populations. This scatterplot displays data from a continent-wide meta-analysis, showing pregnancy and twinning rates dropping linearly as latitude decreases toward the equator. The massive carrying capacities and high twinning rates of the Alaska and Yukon core populations stand in stark contrast to the highly constrained reproductive output of the Shiras edge populations. That lower baseline is not an anomaly. It is a permanent physiological reality of living at the thermal edge of a species range. A species pushed to its equatorial limit sacrifices its reproductive elasticity entirely. It operates with zero margin for ecological error. That lack of elasticity dictates the results of forecasting models projecting Utah moose abundance under future climate scenarios. This forecast graph projects abundance under standard greenhouse gas concentration trajectories, specifically RCP 4.5 and RCP 8.5. Both show flattened, vulnerable population trajectories. The models also reveal that these populations are incredibly sensitive to human harvest rates. Even minor overharvesting mathematically crashes the simulated populations. Traditional wildlife harvest models assume that hunted animals leave behind more food for the survivors, who then simply breed more to replace the lost individuals. But at the range limit, that assumption fails, because compensatory reproduction is thermodynamically choked by the environment. Managing cold-adapted megafauna at their southern limit requires abandoning core population assumptions. Survival depends entirely on conserving maternal energy reserves in an increasingly warming landscape.